Assalamualaikum and hi everyone. In today's lesson, you will learn part 3 of chapter 3, which is Gauss theorem. Okay, just for a quick recap. Okay, Green's theorem states the relationship between line integral with two-dimensional surface. Okay, for Stokes theorem, state the relationship between curve or line integral with two-dimensional surface. And for divergence theorem or Gauss theorem, state the relationship between surface, surface of this solid figure, or solid region with volume integral. With this volume. Gauss theorem, also known as divergence theorem. This theorem states that the total flow or flux of a vector field across the boundary surfaces is equal to total divergence of the vector in the solid region V. Let's say we have this solid region. So total flux of vector field across all the surfaces in this solid equal to the total divergence. So total flux means you consider all the surfaces for this solid figure. For example, this is the first surface. We have 1, 2, 3, 4, 5, 6 surfaces. So total flux, going through this all the surfaces. All the surfaces equal to total divergence or volume of this solid region. Let's look at the definition. Let S for surface be a closed, piecewise, smooth surface which is the boundary of solid region V. Let's say we have these surfaces, this solid region. So this is S, be the surface, be the boundary, boundary of this region. So we have this boundary with this surface and also this surface. We have 3 surfaces, 1, 2, 3. So S be the boundary of this solid region V. So V is this region, is this solid region with normal vector pointing outward, meaning this normal vector pointing outward, keluar, pointing out. And we have vector F, P, Q and R, where P, Q, R have continuous first partial derivative. Then Gauss theorem is defined as this is surface integral equal to, this one is volume integral. So this one is total flux going through the surfaces equal to volume integral of this solid region. Divergence F given by this formula. Or divergence F equal to del dot F. Okay, del equal to del over x, del over y, del over z, dot with vector f. Okay, before we proceed, let's look at normal pointing outward. What is normal pointing outward or out? Okay, let's look at this, the first figure. Let's say we have, this one is cuboid. Okay, normal pointing outward means that, and here the unit normal is pointing out. Okay, out from this surface, okay, out. This one is also out, okay, outward, out. Okay, so if we consider this surface, okay, the front surface, okay, the unit normal is follow positive orientation. Okay, here also we have front, up, and right is positive orientation. Okay, for below, left, and also back follow negative orientation. Okay, let's look at this figure. Okay, normal pointing outward, also the unit normal is pointing out. Okay, keluar. So here for this surface, okay, this surface, the unit normal is pointing out and follow negative orientation. So this unit vector here is negative orientation. Okay, but for up this paraboloid, the surface, the unit normal follow positive orientation. Okay, but if we have this type of paraboloid, okay, this surface, this circle, okay, the unit normal follow positive orientation, okay, up. Okay, but for paraboloid here, this surface follow negative orientation because it is pointing down. Okay, for this figure, tetrahedron, okay, this surface, the unit normal pointing outward is this one, which is positive orientation. Okay, these are the steps to solve Gauss theorem. Okay, we have left hand side. Okay, the surface integral refer to left hand side. This one is for right hand side. This one is the volume integral. Okay, right hand side. Okay, the first step is to sketch. Okay, you have to sketch your graph or your figure or your solid region. Okay, then refer to the question. Evaluate or verify. If the question asks you to evaluate, then you must solve one side only. Okay. If the question asks you to evaluate this one, then you must calculate the right hand side. If the question asks you to evaluate the right hand side, then you must calculate this one, the left hand side. Okay. If the question asks you to verify, then you must solve both sides. You must show both sides. Okay. Step number 3, determine the surfaces or the volume. Depends step number 2. Depends on step number 2. Okay, if you want to calculate left hand side, which is the surface integral, okay, first find this unit normal. Okay, we know that for Gauss theorem, the unit normal must be outward orientation, okay, pointing outward. It can be positive and it can be negative. and then calculate dot product of vector f and n. And step number 3, solve the integration. Okay, if you want to calculate right hand side, the volume integral, okay, first you must calculate divergence of f. Here, divergence of f. Okay, calculate divergence of f, and then substitute divergence of f in the formula to find the integration, to find the integral. Okay, let's recall how to solve surface integral for parametric surface. Okay, for parametric surface, we have cylinder or sphere. Okay, remember, for cylinder and sphere, okay, unit normal and this one given by this formula, del S over magnitude of del S, and then follow this step. Okay, you must convert the coordinate to polar coordinate. Okay, polar coordinate of cylinder, polar coordinate of sphere. Okay. For non-parametric surface, for example, tetrahedron, paraboloid, cuboid, circle. Okay. For the unit normal, you must refer to table 2.4. Okay. After that, calculate the dot product of vector f and also unit normal, and follows the this step. Okay, remember, for paraboloid you must convert to polar coordinate first. Okay, next, we recall about volume integral. Okay. Okay, for cuboid or box or cube, okay, dv given by, okay, so we know that we have triple integral and dv here. So dv follow dv equal to dx dy and dz. Okay, for other surface, cylinder, paraboloid, sphere, okay, dv is given okay by this formula, or this one. Okay, let's look at example 1. Okay, verify the Gauss theorem for this vector f, where surface S is a cube. Okay, so for cube, all the length of this cube for x, y, and z equal to from 0 to 1 is the same. The length are the same for x, y, and also z. Okay, with outward orientation. So we know that this figure or the unit normal follow outward orientation. So the first step is to sketch your figure or your solid region. Okay, we have this cube with x from 0 to 1, y 0 to 1, and z 0 to 1. Okay, step number 2. Okay, from the question, okay, the question asks you to verify. Then you must show both sides, which is f and ds. This is left hand side equal to right hand side triple integral of divergence f dv. Okay, first show left hand side. Okay, show left hand side. Okay, we have this cube. Okay, for this cube, we have 6 surfaces that you must consider. Okay, so let this surface we let as S1. So we have this one is S1, surface 1. Okay, this one is surface 2, and then up is surface 3. Okay, at the back is surface 4. Here is surface 5, and below is surface 6. So you must consider all the surfaces of the figure. Okay, we want to calculate the surface integral of f dot n ds. Okay, the first step is to find unit normal n. Okay, using this table, because cube is non-parametric surface. So n equal to, so look at surface 1. We have, okay, this surface. So here at this surface, x equal to 1. Here at this is surface 1. So here we know that x equal to 1. Okay, x equal to 1. Yeah. And here is y, and this one is z. Okay, y, z. Okay, look at your table. We have x equal to 1. So you must refer this one, x equal to some function. And then for this surface, unit normal is follow positive orientation, because it is front surface. Okay, positive. So here we follow this formula. We have x equal to 1. So n equal to, here I, 1, negative x over y. So 0. X over z also 0. So unit normal equal to 1, 0, 0. Or I. Okay. Then we calculate f dot n. Okay, f dot n equal to, okay, f vector f is 2x, 3y, and z square. Dot product with 1, 0, 0. Okay, and then solve, you will get 2x. Okay, we know that x equal to 1. X equal to 1, substitute, okay, you will get 2. Okay, next, solve, integrate. We have 2 ds. Here ds equal to, ds is dy and also dz. 2 dy dz. Okay, the limit for y is from 0 to 1. Limit for z, 0 to 1. 0, 1, 0, 1. Okay, then you integrate. Okay, the final answer will be equal to 2. Okay, this is for surface 1 only. This is surface 1. Okay, let's look at surface 2, which is this one. Okay, right. Draw the surface. Okay, here we know that here this is the surface. Okay, it is on y equal to 0. Here we have, this is x. Here, this is x, and up is z. So we know that ds equal to dx dz. Okay. and then find n. Okay, for this surface, the unit normal is outward. Okay, outward. So here, outward. Since the unit normal is follow this direction, so it follows negative orientation. So look at the table where we have y for y and also negative orientation. We will get negative j or 0, negative 1, 0. Okay, then calculate f dot n, 2x, 3y, and z square. Dot product with 0, negative 1, 0. We get negative 3y. Okay, but y equal to 0. You will get f dot n equal to 0. Okay, if you integrate 0 ds, which is 0 dx dz, you will get 0. Okay, so this step applies for other surfaces. Surface 3, S3, surface 3 on top, surface 4 at the back, surface 5 here, and also surface number 6 at the bottom. Okay, then you will get this answer. And after that, you calculate total flux. Okay, total flux of all the surfaces, you will get 6. Okay, this is for left hand side. Okay, we want to calculate surface integral. Okay, for right hand side, okay, show right hand side, which is the volume. Okay, first step is to calculate divergence f. Divergence of f equal to del over x, del over y, del over z, dot product with this vector 2x, 3y, and z square. Okay, dot product. Okay, differentiate 2x over x, you will get 2, okay, and 3y over y plus 3, and z square over z plus, we get 2z. Okay, then you will get 5 plus 2z. Okay, step number 2, okay, substitute in the formula. Divergence f is 5 plus 2z dv. Okay. So here we know that dv equal to dx, dy, and also dz. Okay, then determine the limit for x, y, and z. Okay, for this figure it is quite easy. Okay, so x is from 0 to 1, y is from 0 to 1. Okay, and for z is from 0 to 1. 0, 1, 0, 1, 0, 1. And then you integrate. Okay, final answer will be 6. Okay, so when you compare both method or both sides, okay, you can see that it is more easier to calculate the flux using this volume integral. Okay, you will get the same answer. Okay, let's look at example 2. Okay, given vector F, where surface S are the closed surface of the solid region bounded by Z from 0 to 6, and this equation x squared plus y squared equal to 9, okay, which is the cylinder. Okay, use a Gauss theorem to evaluate the surface integral with outward orientation. So the question asks you to evaluate the surface integral. Then you must find the volume integral. Okay, first step to sketch the figure, the region that you want to calculate. Okay, then step number 2, okay, evaluate surface integral. Then you must solve the volume integral. Okay, first calculate divergence of F equal to del X, del Y, and so del Z dot product with F. F for this question is 4x, 3y, and Z. Okay, then we get 4 plus 3 plus 1 equal to 8. Okay, step number 2, substitute divergence F in formula. Just add 8 dV. Okay, look at the figure. So we want to find volume of cylinder. Then dV for cylinder is given by this equation. Okay, or by this formula, R dr d theta dz equal to 8 R dr d theta dz. Okay, then determine the limit for R, theta, and also Z. Okay, so for R is the radius from 0 to 3. Theta is the angle, okay, from 0 to 2 pi. Z is from 0 to 6. Okay, it is quite obvious. And then substitute in the formula. We have 0, 3, 0, 2 pi, and also 0, 6. Okay, and then solve. Here, R here, do not substitute with 3. Okay, because we want to find the we have the R here. Yes, remember that. Okay, then after you integrate, you will get 8R square over 2 from 0 to 3 d theta dz, then 36 theta equal to 72 pi dz over 0.6. Okay, and then this is quite easy. Okay, final answer will be 432 pi. Okay, so to find the flux, okay, going through this cylinder, okay, it is more easier to calculate it using Gauss theorem. Okay, using the volume. If you want to find the total flux through all the surfaces, okay, you must calculate these three surface, 1, 2, and also this 3. Okay, this surface. Okay, we have 3 surfaces for cylinder, so it is more easier to calculate the total flux by using a divergence. Okay, so that's all for today's class. If you have any question, you can ask me. Okay, thank you guys.